Welcome to another unit in this Excel course. This time we're going to learn how we can use Excel to work with random variables which follow a binomial distribution. Well, what does this mean? Well, here first I've written down what generally the situation is for us. So imagine I have a box. Box has red balls, blue balls. Certain percentage of the balls are red. Let's say here 40%, so the rest is blue. Now I'm drawing a sample from this. A sample, let's say I'm drawing 10 balls. And I want to know how many of the balls, what the probability is if, let's say, 3 of the balls are actually red. So let's call this here number red. So if 3 are red. Well, this depends on, the result depends on whether after I draw one ball and check which color it is, I put this back into the box. That's what we call replacement. Or I leave this out of the box, which we call no replacement. Why is this important? Because, well, these chances here, this distribution of red and blue balls, this remains the same if I replace the balls. So I will always have like 40% red balls, 60% blue balls if I replace them. If I do not replace them, with each draw, those probabilities here change. That's actually the big problem here. If they change, I basically have a new distribution every time I draw. So this will be a bit more problematic. Well, more problematic, not for us here in the context of Excel, but this is a different approach. That's what we use the so-called hypergeometric distribution for. Here we start with the easy version. We're replacing them every time. So our distribution remains the same. Well, we could also do this with a different example, except the box with red and blue balls. Imagine you have a dice. You can roll a 5 or something else. Well, the chance of rolling a 5 is actually 1/6. The chance of rolling anything else is 5/6. Then you can do the same thing. Well, if I roll the dice once, I roll a 5. This does not impact my chances here of rolling a 5 again. It's not like once I roll a 5, I will never be able to roll another 5. So here the probabilities also do not change. The distribution also does not change. So if I work with a dice, I can also use the binomial distribution. Of course, the probabilities here do not change. However, let's get back to our example with the box. As I said, here I want to do the example. Sample size 10, so I'm drawing 10 balls. 3 of them should be red. I want to know the probability of this situation actually occurring. If I want to do this, I can simply use my binomial distribution. So I just start typing binom, and I see here binom distribution. Here, I'm working more or less my way back upwards. So I start with number S, which is the number with the characteristic. Then I have trials, so sample size. And finally, my probability. So here I'm interested in red balls, so it's 0.4. Then I only have to decide, is this a cumulative function I'm using or the probability function? Well, here I'm interested in exactly 3 balls. So I'm using the probability function, so I have to put in false. If I'm doing this, I get a result here that I have a chance of roughly 21.5% that in a sample of 10, 3 of the balls will be red. Okay, this so far is good. You can do the same thing with the dice. So for example, imagine I'm rolling the dice, well, let's say 100 times. What is the chance that 10 of my throws will actually be a 5? So again, I can use binomial distribution. This is again the 10, trials 100, probability 1/6. I'm again looking for exactly 10. So I'm using false here, as I'm using the probability function. I get here the chance of rolling exactly 10 5s is roughly 2%. As I said, in all those cases, I'm working with exactly 3 balls are red. Exactly 10 dice throws turn out 5. What if I want to have like at least or at most? Well, what I calculated here in this case is actually p of x being equal to 3. Probability that our random variable gets a value of 3. Here, p of x being equal to 10. Now, if I have like at most, so basically reading here, at most 10 of the balls are red. At most 3 of the 10 balls are red. This would read as x being smaller or equal to 3. This would be more or less almost the same function as before. It would still be binom distribution, the 3, then 10 trials, oops, wrong part, number in the sample 3, I have to replace this correctly, number in the sample 3, number of trials 10, and a probability of them being red 40%. However, when I'm talking about smaller or equal to, that's where I'm using the cumulative distribution function. So here I'm simply putting a true. So I see the probability that at most 3 of them are red is roughly 38%. I can do the same thing with the dice. If I want to have here at most 10 of the dice turn out to be 5, would do the same thing as before. So I can just copy this, but instead of having false here, I would switch to true. And get here roughly 4.27%. Okay, so far so good, but what if I actually have the opposite? If I have larger or equal to 3? Well, in this case, I have to turn this around. Well, what's the opposite of larger or equal to 3? Well, it's smaller than 3. So, as I know that in the end, I can only have 100%, 100% is 1, this probability up here is nothing else than, more or less, this probability. And well, smaller than, really smaller than, is nothing else than being smaller or equal to 2, because I can only draw 2 or 3 red balls, nothing in between. So I'm working with a discrete distribution here. So at this point, this one translates into this. So here I'm simply going with 1 minus, and then I can start binomial distribution. Again, S is 3, 10 trials, probability 40%. Cumulative function, yes, because I have a lesser or equal to. So the probability of having 3 or more balls is actually roughly 62%. The same thing can be done then here for the dice as well. The probability of the dice throws being larger or equal to 10 can be turned around with 1 minus x being smaller than 10. This is actually 1 minus p of x being smaller than or equal to 9, the next smallest one. And well, this I can then put again here, 1 minus, again I use binomial distribution, 10 numbers with the characteristic, 9 numbers with the characteristic, 100 trials, probability of 1/6, and true. Giving me here a chance of roughly 97.87%. Let's check if I did this here correctly. Here at this point I have to check, I have to switch this. I had the 3 here, this should be 2. So yeah, now it's actually correct. So I cannot just copy this. I have to take care that it's not the 3 here, but it's 2. So this becomes 1 less if I turn this around. So when I want to use the cumulative probability function, I always have to write this in the way as smaller or equal to. And that's the important part. It needs to be here lesser or lesser than, and it needs to be the equality case. So it needs to be lesser or equal to, not really lesser than 3. That's actually the important thing here to consider. When I use here the binomial distribution function with true, this is for lesser or equal to. If I use it with false, that's for equal to. And if I have something with larger than or with really smaller, really larger, then I'm going to have to change this to look in some way like this or like that. And well, that was quite a lot to be done, but this basically means that at this point, if you just come up with any 3 numbers here, you can do a lot of different exercises based on binomial distribution simply by just changing the numbers and having here those things adjust them automatically, or calculate your own probabilities you might be interested in. And well, this then concludes the session on the binomial distribution. And if you want to see more on how to use Excel for statistics and other stuff, feel free to visit the rest of the course or have a look at the corresponding playlist. I say goodbye and see you next time.